Okay, the last part of thermodynamics, we're looking at graphing, heating and cooling curves. Heating and cooling curves show us how temperature varies with time when I am having a substance go through phase changes. So in this case, we're looking at a heating curve because the temperature starts out low and we are increasing as time goes by. So time is our horizontal axis, temperature is our vertical axis. We have a single substance. This case it is water because we know that we have 0 degrees and 100 degrees and the horizontal portions are at those temperatures, so we can make the fairly safe assumption that we're dealing with water here. As the temperature of a substance changes, so in this region here temperature is changing, in this region here temperature is changing, and in this region here temperature is changing. These are all single phase. So this phase is solid, this phase is liquid, this phase is gas. Temperature will only change in a single phase. And if we wanted to figure out how much energy is necessary or is required to change the single phase from one temperature to another, we're going to use the specific heat equation. Okay, we've worked with it many times. It's Q, the heat of the reaction, equals the mass of the substance times its specific heat times its temperature change. The equation stays the same. What varies is the specific heat. The specific heat of ice is not the same as specific heat of liquid water, and both are different from the specific heat of steam. So you have to make sure you know what phase you're in so you know which specific heat to use. Where the temperature is constant as time goes on, so in this region right here and in this region right here, we have a phase change occurring. In this phase change, we're going from a solid to a liquid. In this phase change, we're going from a liquid to a gas. When a phase change occurs, the temperature stays constant. All that heat energy going into the system is going into disrupting bonds, disrupting attractive forces between the particles, rather than causing them to speed up and move faster. So during a phase change, temperature is always constant. If I wanted to figure out how much heat energy is necessary to complete the phase change, I'm going to use the equation shown here. So Q, the heat of the energy, equals the heat of the phase change. So solid to liquid, it's heat of fusion. Liquid to gas, it's heat of vaporization. And I'm going to take that times either the moles of my substance or the mass of my substance. That depends on whether my heat of fusion, my heat of vaporization, is joules per gram, kilojoules per gram, or kilojoules per mole. That will tell me which quantity I use for the M, mass or moles. So I want to find out how much heat energy is necessary to take 10 grams of water from minus 20 degrees Celsius to plus 115 degrees Celsius. So I start here. This is minus 20 degrees Celsius. I end here. This is 115 degrees Celsius. So how do I go about figuring that out? Well, I've got 5 equations for the 5 different parts of my graph. So I want to find the heat involved in each part of my graph, and then I'm going to just add them all together. So I start out with 10 grams of water. Specific heat of ice is 2.069 joules per gram degrees Celsius. And my temperature change from minus 20 to 0, the freezing point, delta T is 20 degrees Celsius. Take those numbers, multiply them together, I get 413.8 joules. All my answers are going to be in joules. Next phase, I am melting. So, heat of fusion is 18.49. In this case, it's joules per mole. So I'm going to take my mass of 10 grams, divide by the formula mass of water, that gives me moles, and I'll end up with 10.26 joules to melt all of my ice. Now I have liquid water. I'm going to heat the liquid water from 0 to 100 degrees Celsius. That gives me a delta T of 100 degrees Celsius. So I'm going to take same mass, specific heat of liquid water now, delta T is 100 degrees, and I get 4,184 joules. So I've got 3 of my 5 done. Now I hit the phase change from liquid to gas. I'm going to boil the water. So, next equation. Heat of vaporization for water is 125.16 joules per mole. So I'm going to take, again, my 10 grams, divide by the formula mass, get to those moles of water again, and I'll find out how much heat energy is required to go from liquid to gas for water at 69.46 joules. Last step, I'm going to take that vapor now from 100 degrees Celsius to 115 degrees Celsius. So single phase, back to my specific heat equation. So there it is. 10 grams times specific heat of steam times my delta T, 15 degrees this time. Multiply it together and I get the amount of energy needed to get to my final temperature of 115 degrees Celsius. Now from start to finish, how much energy does it take? I'm just going to add these 5 equations all together. And when I do that, I get 5,301.72 joules. So when we're looking at heat motion, heat storage, thermodynamics, we have a variety of ways to take a look at it, and this gets us through the information we need and gives you some examples that you can base your learning and further homework on.